The conversation about explainable AI today almost always includes references to LIME and SHAP. Many of us turn to LIME and SHAP for insight into models and to ensure that our models are free from bias. So it is a fair question to ask if LIME and SHAP explanatory tools are well equipped to detect bias. Can LIME and SHAP be intentionally fooled by a biased classifier so that the bias is not detected? Everyone, and thanks for joining us. My name is El-Sharif, and I am a steering committee member at Aggregate Intellect. Today, we are very pleased to be hosting Dylan Slack. Dylan is a second-year PhD student at UC Irvine Department of Computer Science, where he is advised by Professor Samir Singh, and he also collaborates closely with Professor Hima Lakkaraju at Harvard University. His research focuses on machine learning safety, spanning explanation techniques, debugging, privacy, and fairness. Dylan will be presenting his paper, Fooling LIME and SHAP, Adversarial Attacks on Posthoc Explanation Methods. To the audience, please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn over the presentation to Dylan. Please take it away.
Hey guys, thanks so much for having me on. It's really great to talk about this work. So my name's Dylan. I'm going to be talking about our paper from last year, Fooling LIME and SHAP, Adversarial Attacks on Posthoc Explanation Methods. This work is in collaboration with some of my great collaborators, Sophie Hilgard, Emily Jha, Samir Singh, Hima Lakkaraju. And this research was done both at UC Irvine and at Harvard University. So machine learning is being increasingly used for a variety of critical settings. So things like healthcare or law. Settings where it's important to have a model that's accurate, but also makes decisions for the right reasons. And when we're thinking about deploying models in these high-stakes settings, it's really appealing to turn to simple classes of models, things that are easy to understand just by looking at them. If you take like a linear model, for instance, sometimes you can just inspect the weights of that model in order to figure out what it's doing and why it's making certain decisions. You could say the same thing about decision trees. Sometimes if you just look at the nodes on a decision tree, you can get a sense of why it's making certain decisions. And again, this is really appealing for some of these critical safety concern settings because we want to trust that and know that the model is making the right decisions for the right reasons and for reasons that we can understand. Sometimes, however, there's this trade-off between simplicity and complexity. Sometimes complex models can do better on tasks. So things like neural networks or random forests, you can get higher performance according to metrics like accuracy. But this can come along with a bit of a trade-off in terms of like interpretability or how well you can understand what this model is doing. So if you look at like a random forest, for instance, it's hard to understand like why it's making certain decisions just from looking at a bunch of decision tree stems. The same thing for neural networks. So what people have done and why post-hoc explainability is a thing is they've built these complex models and then realized that we can offer explanations for those models using very simple classes of models. So we build our complex model, we get good performance according to something like accuracy, and then we use another model after the fact to explain what that complex model is doing. And this is really what post-hoc explanation is. So we have our neural network, but we use a linear regression to explain one aspect of that model to try and make it a bit more interpretable and give us the tools to understand what it's doing in this high-stakes setting. So in this talk, I'm going to be specifically talking about a few types of post-hoc explanation techniques. I'm going to be talking about vulnerabilities in those techniques, but I want to introduce us to this class of techniques just a little bit more before we get going on that. So post-hoc explanation methods typically consider these complex models as black boxes. They don't, a lot of the time, they don't look at the internal details of the model. They only require query access to that model, so they can ask the model what the output is for specific inputs, but they don't really get that much more than that. There's different flavors of post-hoc explanation techniques. There's local, there's global approximations. Local approximations just explain individual inputs. That's what LIME and SHAP are. There's global approximations that look at the model on the whole and try and offer an explanation. And then there's gradient-based versus perturbation-based. Gradient-based uses some sort of gradient signal to offer explanations, and perturbation-based relies on sort of perturbing a data instance to get a sense of what the model is doing locally around that instance. We're going to be focusing on this local perturbation-based style of explanation. And this generally includes techniques like LIME and SHAP, and really any other local explanation technique that works by taking an instance, perturbing that instance, and then fitting a local linear model, like what LIME and SHAP did. Now, just to situate us in the sort of the discourse on these methods, LIME and SHAP were proposed a couple years back, but since then, people have been figuring out that these techniques might not always be the most reliable. So there's been a body of work that shows that if you take something like LIME and rerun it a couple of times, you might get drastically different explanations. This is due to the sampling instability associated with LIME. Sometimes when you take LIME and just perturb a point by just a little bit and then rerun the explanation, you might get a really different explanation. So it's not that robust. And this brings into question like the trustworthiness and reliability of these methods. That said, there's not a ton of work that really thinks about this from an adversarial perspective. So in these other works, they've sort of said what's sort of intrinsically might be wrong with LIME, but we're going to say what can an adversary do to sort of try and game these techniques to intentionally manipulate them to produce bad explanations. And this is where our paper comes in. We propose a method to do this. We find that we can game these explanation techniques. And we look at a couple assumptions of these methods that really produce this result. So what we provide in our paper is a method that allows you to train a model that is accurate on the data. It does what you want it to do on the data. This could be using some trained linear model. This could be deploying some other rule set that you've come up with. But techniques like LIME and SHAP will not explain this. LIME and SHAP will explain some arbitrary other function you've set up. This could be another set of rules. This could be another linear model, really anything else. So this is what this paper is going to show. We're going to do this through the lens of masking discriminatory biases in black box classifiers. So this is sort of like our motivating example, why this might be a big deal. But really, I want to emphasize that you could use this in any setting to mask any sort of decision that your classifier might be making on real data. So to go back to both of these types of explanations, LIME and SHAP, both of these fall into this model agnostic local explanation class. So just to repeat what that means, both of these techniques don't make any assumptions, or LIME and kernel SHAP both don't make any assumptions about the type of model, and they offer local explanations, meaning they take an individual point, they sample locally around that point, and then they fit a weighted local linear model in order to offer a local explanation. And they sort of have different ways of doing this, but they're very similar overall. And what they provide are feature attributions. So what this means is that if you have a test like loan prediction, and some of the features like how much someone makes or their credit score might be really good indicators of whether they're gonna default or not, feature attribution methods would rank these two features highly. They would just assign them a big number. So we're really going to be gaming these feature attribution numbers. So this is an illustration of this local sampling stuff that I've talked about. And this is where the vulnerabilities in these methods are going to start to come in. So this is from the LIME paper. What this illustration is saying is that this blue region is one class or decision class, and this pinkish region is another. And LIME is offering an explanation for this red sort of bold plus sign here. And what it's doing is it's picking points locally near this point. It's upweighting those points that are closer and then fitting a weighted local linear regression. So even though this model is complex globally, we can fit a local approximation that's pretty good for this point. And this is what our explanation is. And one thing to note here, one thing I want to note is that for LIME, it does this through sort of a simple set of heuristics. It takes a point, draws from a normal distribution scaled by the range of the feature, and then it uses these perturbations, and it sort of flips categorical variables randomly. And kernel SHAP has a different way to do this. They require users to give what they call a background distribution. And really what this is it's a set of numbers that are going to be substituted in to a particular data instance in order to create the perturbation. So if my background distribution was 0, 0, 0, and I had a data instance that was 1, 2, 3, it might pop in 1, 2, 0 or 1, 0, 3 or any of these to create a perturbation, but it's always drawing on that background distribution, which you could set to whatever you want it to be. So the thing about these perturbation methods is that they tend to create data points which don't fall in the true distribution of the data. And this turns out to be an issue. So we can visualize this. And you can sort of imagine why this might be the case. If you take a feature that you treat as numerical, like age in LIME, you draw from a normal distribution and you get like 20.2 years, that clearly will never occur in the real world. So we're going to exploit things like this, but it holds more generally than that. So this is the COMPASS data set. These blue dots are the original COMPASS data points. So COMPASS is a data set that has to do with rearrest prediction. So these blue data points are the original. This is PCA. These blue data points are the original COMPASS data points. And these orange dots are the LIME perturbations. So we run the LIME perturbation function on these blue dots. And then we do PCA. And what you see is that there's this big difference between the orange, the LIME perturbations, and the original COMPASS data. So this might be an issue for this technique. Because if you're thinking about how to do an attack, you could have one decision function on this original data, but you could also use some sort of other decision function on the orange data. And LIME would effectively be explaining the decision function on this orange data, but in reality, you'd be using some sort of other set of rules on the real data to do whatever you want. And this is the insight, the key insight that we're going to exploit to build our adversarial models. This fact that just to emphasize it, the perturbations aren't always in distribution, and you can use two different models, one on the perturbations, another on the original data, to have LIME explain one thing when the real classifier is doing something else. So as I'm going to get into how we're actually building this attack, but I also want to give a little bit of motivation on how we see something like this being used. So let's say that an adversary wants to deploy some sort of bias classifier. Let's call it F in the real world. So to concretize this, let's say that the adversary wants to deploy a classifier that says something along the lines of, let's only use race to make decisions. So that's literally take an if statement on the race feature and then use that to make our decision. At the same time, the adversary maybe needs to provide black box access to customers or regulators who are going to use like post-hoc explanation techniques like LIME and SHAP to try and understand why certain decisions were made. So hopefully in this case, if you took this totally biased classifier F, LIME would say, yes, 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 race is the most important feature. It's so important. Bad stuff is going on, and you'd understand that. So our goal is going to be to hide this. Our goal is going to be to use this exploit of the difference between the perturbations and the original data to hide these biases. So what we're going to do is we're going to train these two models, one model that's fair on the perturbations, and then another model that is racist or bad on the real data. And I sort of think of this as like a Trojan sort of horse-esque style of attack. You have this LIME, and it's only looking at this fake data, but in reality, it's being sort of like racist or discriminatory in the real data. It just doesn't can't figure that out. So maybe this isn't maybe you think this isn't necessarily like realistic or might not occur in practice, but I really see a lot of parallels to this style of attack to like real situations that have occurred, like the Volkswagen scandal. I'm not necessarily like an expert on this, but from what I understand, Volkswagen installed a device on their cars that sort of knew it was being, they were being audited or tested, and then it changed something about the cars so that auditors like couldn't figure out that it was doing something bad whenever it was deployed in like the real world. So in a similar way, so our attack is very similar to this. You have some sort of discriminatory model that's being used on the real data, but for all the perturbation data, you're using another model. And this is really what LIME or SHAP is testing for. So maybe there's some parallels here. Now, I'm going to talk about how we actually go about building this classifier. So what the adversary is going to do is they're going to provide us with a bias model. Let's again call it F, and then an input data set. This is like real occurring data that they want to be biased on. And what we're going to provide is this, what we call a scaffolded classifier E. And it behaves exactly like F when making predictions on the real data. But whenever you get a perturbation, it's going to use another model. And then this is what I mean by scaffolded classifier. So E is our scaffolded classifier, or adversarial classifier, scaffolded classifier, same thing. And it's just a piecewise function. So if X is in distribution, use the adversarial model F. Otherwise, use an unbiased classifier, call it psi. And biased classifier, think along the lines of like something racist or sexist. And then psi be some other function that you'd be comfortable having LIME display to regulators. So we're going to look at this from the perspective of like uncorrelated features. So we're going to introduce in some of our tests features that are totally uncorrelated with the sensitive feature, and then have it explain these. And what this indicates is that LIME is totally failing to explain like anything associated with the actual prediction task. Now, if you look at this piecewise model, there's one other step here, and we need to actually decide what function to use. Rather, so like if the point is in distribution, use the adversarial model. If it is not, use the other model. So how do we do that? It's pretty simple. What we do is we take the original data given to us. We perturb each data point in that data set using either LIME or SHAP's perturbation function. So we're called for LIME. This is something along the lines of drawing from a normal distribution and adding it to the original point. For SHAP, it's drawing from this background distribution. And then for that perturbed data set, we just create a simple prediction task. So we just create a simple prediction task to identify if the point is in this original data set, is in distribution, or if it's one of these perturbed data points. And then we can just use any model to do that task. So we use like a random forest, for instance, in our paper. Then this random forest, which just decides if the point is in distribution or not, becomes how we make this decision in the piecewise function. Cool. Now let's get on to some experiments. That's basically our technique. It's pretty straightforward to implement too, which is nice. For experiments, we look at 3 data sets. We look at Compass, communities in crime, and German credit. Compass is rearrest prediction, communities in crime is violent crime prediction, and German credit is loan prediction. Each of these data sets have a sensitive feature associated with them. And this is what our bias model is going to rely on. So for all of our bias models, we just take like basically an if statement along the sensitive feature. So like if male, give loan, otherwise deny loan. So we use the standard implementations of LIME and SHAP. And then for this unbiased classifier, this is the classifier that LIME and SHAP is going to explain after attack. We use either synthetic features or existing features in the data set. So for existing features, we just create some other model that relies on some of the real features and then have LIME explain that. With synthetic features, we introduce new features into the data and we purposefully make them uncorrelated with the sensitive feature and have either LIME or SHAP like explain those with the attack. And the reason that we do this is one potential issue with our evaluation is that if you have a feature that's very correlated with the sensitive feature, LIME could potentially be just shifting weight from the sensitive feature to the very correlated feature. And if that's being explained, it's not necessarily clear that you're actually fooling LIME. So just to make sure that we are, we incorporate these like uncorrelated synthetic features. So these are the graphs we're going to be looking at for evaluating our results. So what this means is that this is for the bias classifier F without our attack, and then this is LIME, and how often these features occur as either the first, second, or third most important features in the explanation. So percent occurrence, that's what that means. So the way to read this is that for when you run LIME on the bias classifier, race is listed as the most important feature all of the time. And these other features are listed as the second and third most important features, basically no better than random, sort of as we'd expect LIME to do. But when we introduce our attack, this figure right here, this middle column, is when we use our attack with one uncorrelated feature. So we have psi rely on this uncorrelated feature. And the bias classifier F is still using African American. What we see is that the uncorrelated feature becomes the first most important feature all of the time. And then African American and some other features are listed no better than random. And we take this to mean that our attack is pretty successful. We've basically taken this feature that is uncorrelated with race and said it is the most important feature. And then we do the same with two uncorrelated features. And the difference here is just we have psi rely on both of these features instead of just one. And then we show that the first and second most important feature are these features that we've introduced. So the conclusion here is that we can take this model that is totally biased and then do something, run our attack, and then all of a sudden it's still biased on that original data, but all the explanations are explaining these features that are uncorrelated with race. So that's probably an issue for LIME. Now here is SHAP. So this is for the COMPASS data set for SHAP. And we do the same task for COMPASS. And then we see that race is listed as most important feature for the true classifier, the bias classifier F. So this is the same thing as earlier, basically. But when we run our attack, the uncorrelated features start to look a lot more important. We see for this that race does end up looking like an important feature a lot of the time. So it's not quite as successful as it is on LIME. So it's clear that SHAP is definitely a bit more robust to this, but it still looks a bit problematic. Next, we're looking at the German credit data set. This data set has to do with loan prediction, as a reminder. And here, instead of looking at these synthetic features, we take a feature that occurs in the data, loan rate per set of income, and then we have the unbiased classifier psi rely on this feature. So here's the bias classifier. We see that both LIME and SHAP rely on gender all of the time before our attack, but when you run our attack, we see that loan rate per set of income looks pretty important for both LIME and SHAP. And gender looks definitely less so. So we take this to be a success as well. So that's basically our technique. It's, as a reminder, it's this novel scaffolding technique to hide undesirable biases in black box models. If you take a method like LIME or SHAP, it's going to potentially hide some of the issues that LIME or SHAP should be discovering. And sort of before I end here, we noticed that there was some difference between the ability of LIME to prevent these and the ability of SHAP to prevent these attacks. And it really just comes down to this perturbation function. And it comes down to how many of the perturbations look like the true distribution of the data. So with SHAP, because you have this background distribution, the perturbations are basically a bit less random, so they look a lot more like the real data. And this makes it harder to train this scaffolding classifier. So that's basically why it doesn't quite work as well. But with LIME, it tends to work very well because they do something very simple like perturb with random noise. So this is applicable to LIME and SHAP, but more generally, this could work on any perturbation-based explanation method. So something to keep in mind with these methods in the future. So thank you.
Thank you, Dylan, for that great presentation. We will now start the Q&A part of the session, and we will be presenting Dylan with live questions, as well as questions we have received in advance. So the first question, Dylan, is, first of all, can you hear me? Just doing an audio check.
Yep, can hear you well.
Okay, excellent, excellent. So the first question we've received from Abelish, he is sort of questioning whether LIME or SHAP are failing to explain a model, because we're essentially constructing two different models, and he's just questioning the analysis in the sense of, are we really looking at one model that we're failing to explain, or are we just being asked or being fooled into looking at a completely different model in the out-of-sample distribution?
Yeah, so we're being fooled into looking at a completely different model. That is, I think, a correct analysis, but I'd still argue that that's a big issue, because I think there is an expectation with both LIME and SHAP that when you ask for an explanation, it's going to give you an explanation that is relevant to what the model does on the real data. So yes, we're explaining, like, I guess, a slightly different model, and in some sense, like, LIME isn't failing in that way, but in like another sense, I do think it is failing because of this idea that we should have an explanation that actually tells you something about the way the model behaves on real data. Otherwise, it's not really that it's not like super insightful in some sense.
Okay, excellent. Thank you for that explanation, Dylan. Now, the next question we've received from Jacob is, what baseline is being used when calculating SHAP values? I suppose he's wanting to clarify if you're using kernel SHAP or a different, so can you just clarify what baseline of SHAP that you've used? Yeah,
so for SHAP, we're using kernel SHAP. Again, this attack is for like local perturbation-based explanation techniques. So there's these other variants of SHAP, like tree SHAP and stuff like that, that won't fit this general mold. Yes, we use kernel SHAP, and then we run it with the k-means background distribution. There's a lot of other potential choices in the background distribution that could lead to different results. But that is the choice we made in the paper.
And then another question from Jacob here is, it's more of a general question, is how much of the success,
and then another question, success, how much?
Okay, that's with an echo. Let me get rid of that. I apologize. How much of the success of your attacks is due to the weakness of these explainable algorithms? So could you just make a broad statement, and do you consider this to be a general weakness of post-hoc perturbation-based methods?
Yeah, I do think it is. In some sense, it is a general weakness of these methods. So what these explanations like try and say they're doing is like to explain, they offer an explanation for any model. And when you make like a big broad claim like that, you have to make a lot of like additional sort of assumptions about how you're going to do that. And if you don't ask for like characteristics of the data, which a lot of these techniques don't really want to, you're going to fall into this trap where a lot of the like perturbations might be out of distribution, and that's where attack comes in. So it really, in some sense, you need to start to make a lot more assumptions about how you craft these perturbations and be a lot smarter about how you do that in order to not fall into this trap, which might require a lot more knowledge about what your data looks like.
Okay, so this is super interesting, Dylan, because the more generic the explainer is, I mean, obviously there's an appeal in there to explain any model, but it seems that there are advantages to having model-specific explainers that could just maybe be less vulnerable to these types of attacks.
Yeah, I definitely agree with that sentiment. If you have like posthoc explanation techniques that like look at specific classes of models and to use specific parts of those models in order to generate these explanations, you're probably not going to fall into this issue as much. Even if you take your perturbation-based explanation method and do something like only sample points that occur in your data set, you're not going to fall into this trap, or use a background distribution that mostly draws from the real data set. This attack is just going to be less of an issue.
Okay.
So we had one other, just to make one other comment on that. Mm-hmm. There was one other earlier question that was like something along the lines of, well, SHAP isn't really like, or LIME isn't really failing here because it's explaining some other function. And in some sense, there is a little bit of merit to that, because if you only limit your perturbations to those that occur in distribution, you're not learning anything about what your model does on outer distribution data, which could be potentially interesting to your understanding. So there's another trade-off there.
Okay. Thank you, Dylan. That was very insightful. Now, one question here we have is that SHAP makes theoretical guarantees on the fair allocation of feature importance. Why do these guarantees not protect SHAP from the vulnerability that you've exploited?
Yeah. So we're not really attacking that part of SHAP. All those guarantees still hold. SHAP is just sort of explaining the function you're not interested in. So all of SHAP's like guarantees will hold true on this innocuous function, or psi, as I talked about in the paper. So all of that will still be all good, but it's just SHAP being applied to a separate function.
Okay, excellent. Now, would a global explanation method, even a generic post-hoc local explanation method like the surrogate decision tree, be less likely to be vulnerable to these attack techniques because it's just maybe looking at the broader data set distribution?
Yeah, I think a lot of it really comes down to how you're selecting the points that you're going to fit this global model on. So if you're using only the real data set, I'd say that this is going to be less of an issue. But if you're selecting those points based on like perturbations like LIME does, I don't really expect this issue to go away. So it really goes down to it really boils down to the sampling strategy with this question.
Okay. Let me just see. I think we have a question from Amsi here. Can you give an example of an uncorrelated feature with race?
Good question. I maybe could have been a bit clearer about that. So basically we just take like if our feature is like if the race feature is like binary 0, 1, we just take a random Bernoulli distribution and draw 0, 1. And then we sort of expect those to be uncorrelated because we drew the other one randomly. We drew the uncorrelated feature randomly. We did do some checks to make sure that was the case, and it did appear that they were pretty uncorrelated. So yes, that was really it.
Thank you, Dylan. Yeah. Now, just a very broad question here is, would it be a fair conclusion from your work that these explanation tools we have they can help us identify bias, but they cannot guarantee the absence of bias?
Yeah, I think that's the case. Bias comes in a lot of different forms, and relying on just one method to uncover bias is definitely could be a bit tricky. So when you're using something like LIME, it offers an explanation for an individual point, and if race looks really important or something like that, maybe there's some bias. But that doesn't tell you anything about the global characteristics of the model, of how the model behaves on sensitive data, which could be something that you're really interested in if your goal is really to uncover bias in the model. So yes, this could potentially be one tool, but it needs to be one tool in a broader suite of tools.
Okay, and that was really excellent from a practitioner perspective. That really just diversify the tool sets that you're looking at, and in order to get a broader perspective and broader insight. Now, would it be possible for us to get a brief tour of your GitHub repository to help us identify what's available out there and how we could potentially reproduce the results that you reported?
Yeah, for sure. On it now. Okay, can you see that all right?
I can't because I'm dialing in and I have a bad internet connection today. So if you could, but I think you're probably going to be fine. So let's just go. Go ahead.
Cool. So quick tour of the repository. It's linked through my GitHub account, Dylan-Slack, and it's fooling LIME and SHAP, and I have it pinned to my account page if you're interested in taking a look at it. So what we've done here is we've categorized our experiments. So the communities in crime, Compass experiment, and German experiment into 3 different files. They're very easy to run. You just need to basically just run this file, and that's it. So if you look at like the Compass experiment, this is the whole experiment code. You just need to run this file and it'll start running. It takes a little bit because you need to generate a lot of explanations, but it's really pretty manageable. And what it's going to tell you is these printouts of how often the feature occurs as this rank of the feature. So this is the most important feature, and like the unrelated column, or what we mean the uncorrelated column, occurs like almost 100% of the time. So this is what the printout is going to look like. To make the repository a bit more successful, we've set up, or a bit more like easier to use. If this is going to load, we've I don't know why it's not loading right now, but we've set up a couple like simple walkthrough type things to look at. And that's really about it. Please feel free to cite us, of course. But yeah, pretty straightforward. And then we've put all the models. One thing, I think this technique is really fun because it's really simple to implement. This file is just really a couple hundred lines of code. It doesn't really even need to be this long. And this is the whole attack for both LIME and SHAP. So you can implement it yourself pretty easily. So yeah, that's about it.
Well, certainly there's a treasure trove to look at here, and certainly to try to replicate your results in different settings. Dylan, that was excellent. Before we wrap up, are there any final thoughts that you would like to share with us?
Let's see. Yeah, I mean, yeah, not to. I know I presented an attack on these methods. I still am a fan of local explanation methods. I think they can provide like useful insights into models. I just think we need to get better about understanding when these types of methods are successful, and also be open to new lines on local interpretability research that could give us better techniques. So I will end on that.
Okay, excellent. Dylan, thank you for a great presentation, and I thank all of you who joined us online and submitted questions in advance. To see more free content like this, please visit our website at ai.science and log in to access the slides from this and other sessions. Also, make sure to subscribe to our YouTube channel at ML Papers Explained to get notified about all the live sessions and other free content we publish. This concludes our event. Thank you for watching.
Thank you.